This next topic, we're going to talk about the aerodynamic forces. To start with the aerodynamic forces, I want you to consider the following. I want you to consider an airplane, and there are two ways to consider the airplane. One way is assume the airplane is static and make the air flow around it. The other way is what really happens, where the airplane is moving through air. Now, in most of the wind tunnel testings that we do, even the CFD modeling, we imagine we need to have a huge amount of uh, atmosphere space to be able to move this and put all my test data, my sensors to measure what's happening with my aircraft. So what we tend to do is we like to fix it in a wind tunnel or maybe in a CFD model, computational fluid dynamics, and have the air flow around it, and that becomes an equivalent problem. It becomes identically the same, and that's thanks to the Galilean principle of relativity. Okay, so let's write these concepts down. So there are two ways that we can solve the problem, as I just mentioned. One way is so this is an airfoil, two identical airfoils, or at least assume that they are completely identical. In one case, let's say this case is still air, so the air is not moving. This is mainly the real scenario that's happening to the aircraft. In this particular case, what you have is the airplane is moving at a velocity, and at a certain given point, you're going to have a lift and you will have drag. Going to have lift and you will have drag. Now, in the same scenario, in a different scenario, let's say now here, airfoil is still, and this is typically our testing, the case of test and simulation. / modeling. It's easier to analyze the data like that. So for this particular case, now you have a stream velocity. The stream is moving, the air is moving. And at the same location as here, I'm going to calculate a lift, and I would like to calculate a drag. Okay. The problems here, the problems are completely identical, because what we are interested is in using the relative velocity. Relative velocity is all that matters. And this can be done thanks to the Galilean principle of relativity. Okay. Now, in the same aircraft, you're going to have several. You will have several. In this particular scenario or this scenario, you're going to have an airflow and you're going to have a contact with the plane. So you have your aircraft, okay, and you need to have air contact for this to fly. there's no contact, then there's going to be no pressure at the bottom and at the top, and you want the pressure at the bottom to be higher than the pressure at the top if you want a positive lift, or vice versa if you want a negative lift, you want it to land. So just imagine you have an airplane, you need to have the full contact. To have the full contact, we need to make sure that there is some boundary layer that's generated, and the boundary layer is completely laminar, or we call it smooth enough, then we like that. If it's turbulent or creates many wakes, that actually is disadvantage. It's impossible to design an airplane. It's impossible to design an airplane with a zero drag. You need to have some drag, minimum drag for this to fly. So we want to determine how much of that drag is acceptable, how much of the lift is acceptable. Okay, obviously we want to maximize lift. So let's go back to our airfoil. And what we're going to assume now is, you're going to have a stream of, you're going to have a stream that's coming here. It's probably going to do something like this. Is going to do something like this. Your stream is doing something like this. Your stream looks something like this. So what happened is, let's suppose I am interested in knowing what's happening at one point, and let's take this surface area. Okay, remember this is the airfoil, right? So this is actually part of a full wing, and I am taking a small surface area of that airfoil, and we're going to call that surface area delta S. And to understand this, let's suppose I get a unit normal. I have a unit normal. In that unit normal, I'm going to have a delta, a component, in a force component in the normal direction. That's a resultant of the total force acting in my body at this point. And also I'm going to have here the same point, a tangential component, and the tangential components will be my shear component acting at the same point. So in aerodynamics, the forces that we have, aerodynamic forces, are two forces. First are the normal forces. Okay, so these forces are this forces right here. Okay, these forces are like pressure. You're going to have a constant pressure across your airfoil. It's going to look something like this. You're going to have constant air, you're going to have pressure, probably pressure distribution goes something like this. And it's always normal to the surface. It's at 90 degrees. At every single point is at 90 degrees to the surface. Your pressure distribution is going to look something like that, and we will talk about that in a few minutes. So this is going to produce normal stresses. Okay, and the normal stresses of this pressure is going to be my delta normal divided by delta stress. You will also have a shear stress. You will have also a tangential stress or tangential force. This is nothing else than shearing. This guy over here that's actually trying to resist the motion, and we call this the shear stress. Okay, and we said tau is equal to delta ft divided by delta x. Okay, so with these ideas fixed, I want to talk a little bit about the shear stress because it is important to understand what it's doing. And just imagine you have a flat surface, okay, and the surface is fixed. Um, and you have a stream of velocity, a stream coming at a velocity, let's say u. Okay, so use the stream of the velocity, and what's going to happen here is it's going to create a gradient that's going to look something like this. So as you move away from the surface, you're going to have a constant stream. As you start getting close to the surface, now it's going to be a function of tau. So this and this right here, let me change the colors. Somewhere here, just where it starts being constant, this is called your boundary layer. And just to go ahead of myself, if the boundary layer is laminar, is smooth, there you can think about, you could think having a surface and there's almost zero friction. Okay, that's called viscosity. But in fluids, it's called viscosity. In structures, it's called friction. If you have more friction you have, the more resistant you're going to have the surface, right? Now, in airplanes, you don't want too much friction. You want this to be a laminar flow, as smooth as possible. If you have turbulent flow, then the things are not good. Okay, so laminar flow is good. And then turbulent flow, we cannot avoid turbulent flow, but we can reduce it. So the goal is to reduce. The goal is to reduce this type of load. Okay, so there is between the surface and the fluid, there is mu, and we call that mu the coefficient of viscosity. And the way we find that is, you can see this is coming here, so this will be my delta U, and this is delta U, my velocity. This is delta Y. It actually goes in this direction. This is Y. It is in the Y direction. So then you can show that your tau is equal to the coefficient of viscosity times the U, that's the velocity, times the Y, where this is nothing else than the velocity. This is the velocity gradient. Okay, it looks very nice and fluid here, but the velocity gradient can be very nasty as we move on. That's, for an example, if you had a case in which the flow was not, because you have a high angle of attack, let's say you have a high angle of attack, so now your fluid is coming here, is slightly contacting, but then it starts to separate. In this separation, what's going to happen is, let me draw this better. When you draw, come on. So, and then at the bottom, typically your fluid remains. Can I get this right? I'm sorry about that. This has to stay as close as possible. Then this here generates what we call wakes. These wakes, what they do is they create turbulent flow. Okay, so now here you might have had a very beautiful gradient here your gradient is going to look all crazy because this is completely turbulent. We don't like this, but there's no way to avoid that either. So in fluid mechanics, sorry, given a velocity gradient, a velocity that is flowing here, we are interested in finding this boundary layer. Okay, this is what we call the boundary layer. And the boundary layer is important because it's going to help me better understand what happens. And if I can try to reduce this, it's for my gain. Okay, so this is a great field of research. If you are interested in this, that's something you can study as well. So with this said and done, one thing that we have to realize that both lift and drag are both going to exist. It's impossible to get rid of one, of making this zero. It's not going to be possible. Okay, but they have to exist. And one last thing before we move on. So if I have the boundary layer, this part here where it stops being constant here and it stays constant, this is also known as the region of viscous influence. Okay. So typically the way we are working is we like to work with a Newtonian fluid. And by Newtonian fluid, we mean there is no slip boundary condition. So we are saying is you got the surface. At no given time, your flow is just going to at no given time, your flow is just going to pass through without touching the surface. That's not going to happen. And any single time, what you're going to have is it's going to always make a contact to create some boundary layer. So you will have some contact, and that contact is going to create a boundary layer. Okay, so that's important, no slip condition. The next thing that we want to consider is that the flow remains undisturbed away from the airfoil. Okay, so as I move away from my airfoil, it's going to kind of remain constant. It's going to want to remain constant. Okay, that's what this means. Last item, the varying speed distribution follows the following relationship. Follows tau is equal to mu delta velocity delta speed. Okay, so with those ideas fixed, we can now go ahead and go back a little bit, and let's go ahead and redefine our function, your lift. That was the density, velocity, surface area of my wing, or span area, times L. D is equal to 1/2 rho v squared SCV. This is the coefficient of drag. This is the coefficient of lift. And what typically we have in this quantity that's very, very important, that we can also write this as CL C over D. This comes from testing, and typically we want to make sure this is maximum. you can immediately see that your D can never be 0, otherwise this will blow up. There's always a D. There's going to be a sacrifice that we need to make. And actually, your plane would not fly without without any drag. So if you look at the plot itself, your plot of CL, coefficient of lift, against your angle of attack, lift and drag. So your coefficient of lift looks something like this. Okay, so this is CL, and this will be CL max. This is the location where your aircraft stalls. And then your drag looks something like this. You look something like this. So there is a location where this is minimum, but we care for this location where it intercepts each other. This is CD. So this is the location where it's ideal to fly, because that's the combination, the optimum combination of your plane. The minimum drag for the optimum is the minimum drag possible you can have for, and the optimum lift. If the aircraft stalls, this is what it basically is happening. I want you to consider the aircraft. I told you that every single time there has to be a contact with the surface. Imagine this is flying, it's coming at a high angle of attack. So now your air is coming in this direction, and now you have big waves on this side. So as the aircraft becomes at the higher angle of attack, basically there's a separation of the flow right here. But that separation basically makes your aircraft lose its strength, and it's going to go all the way down. We lost the aircraft. You lost the complete stability. That's called stall. Now, the spacecrafts and the military aircrafts can do that, because to avoid that, they have thrusters, right? This thrust compensate the stall scenario. So now it can go fast enough to avoid separation of fluid and the structure itself. Okay, so that is important. Okay. So in general, your flow is going to look something like this, where you have the pressure distribution, as I mentioned to you, and this is kind of, this will be your distance S. This is the distance S going around your contour. This is your shear distribution. This is the pressure distribution around your airfoil. And we like to, again, reduce the drag, but it's many times it's completely impossible. So this actually completes the first discussion on theory of aerodynamic forces.